screen. If everyone can see, I'll start. So thank you, Tim, for the introduction, and thank you, the Salt Basins Technical Interest Group, for the wonderful initiative of organizing these meetings. I've had a chance of watching some of them live and also the recordings, and they're all very, very interesting. So congrats on that initiative, and thank you for the opportunity to show a bit of the work we've been doing on salt. Not salt tectonics, but I believe this will be of interest to any person working with salt basins, be it in a more academic or more commercial view. So I'm going to talk about salt biostratigraphy, and we'll also see a bit on what can we learn from the thermal maturation of evaporites using the same techniques. So I'll go through briefly the history and methods. So the oldest reference of biostratigraphy of evaporites comes from Hugo Luc in 1913, and he studied the Palynology of Zechstein salts, which was found in onshore boreholes in northern Germany. This was a more or less one-off study. It was not until the 1950s and 1960s when Wilhelm Klaus studied Permian and Triassic evaporites from Austria and Germany, studied mostly the Palynology of several deposits around Germany and Austria, and he published some of these results, and that's how more or less the salt biostratigraphy gained some momentum at the time. Unfortunately, that basically stopped, and you can only find once in a while someone that works with biostratigraphy of evaporites, at least in the public domain. So these are just a few examples of this is the initial work by Wilhelm Klaus, and then there were a few other people that work with salt biostratigraphy, but a bit dispersed over time, and there's no, let's say, consistent usage of salt biostratigraphy, of people working with evaporite biostratigraphy. So recent references to salt biostratigraphy are rare, but we'll see in the end that there's actually some revival of this technique, and hopefully this will become standard in the near future. When you look at references or research for references in the academic domain, they're not a lot. When you narrow down to the oil industry, they're even scarcer. So there's really not a lot published on salt biostratigraphy. There's a few examples of the Paradox Basin in the US, of the Gulf of Mexico, a few stuff from the evaporites in Oman, although here what was actually studied were the carbonate stringers embedded in the evaporites, not the evaporites themselves. There's probably more work done which is buried in confidential reports within companies, but at least in the public domain, the amount of publications that deal with salt biostratigraphy is really, really low. So biostratiraphers usually use standard methods to process samples. Specifically for Palynology, there's a standard method, which we'll see in detail in a minute, which basically is not effective for evaporites. Basically, most evaporites have different mineralogies, or they're composed of different minerals, and the usual techniques that are used for Palynology, and I'm guessing also for other fossil groups, they tend not to work with evaporites. So that may have deterred people in the past, and they may have just labeled samples as barren, when actually they were just not using the correct method. So this, for Palynology specifically, we take a sample, be it an outcrop or cutting sample. We usually clean it and crush it. We do a first acid attack with HCl to remove carbonates, then a hydrofluoric attack to remove all the other minerals. Most of the silicates are destroyed by this, and you get usually a quite pure organic residue. Sometimes you still need a second hydrochloric acid attack to remove any neo-formed crystals or some of the minerals which will not dissolve with the previous acid attacks. Then usually civets to remove fine organic matter, and then you mount slides and you observe them under biological microscopes. And this is how you see, basically are looking at the organic residue that you obtain from a rock sample. This is not new for those of you who work with salt basins. This is a map which is shown very frequently. Salt is commonly present in many petroleum provinces around the world, and it's a main component of the petroleum systems. It's important for trap formation, and this is just an example of the many types of traps that can be formed when you have mobile salt. So above the salt, you can form anticlines, you can have pinch outs against the salts, faults associated with the salts, with the salt body can also form traps. So there's many types of hydrocarbon traps which can be formed associated with the salt body. For the mining industry, it's also important, not just the salt itself, but frequently the cap rock also contains valuable minerals that are explored when they're close enough to the surface and they can be mined. They're also very important for other applications, not strictly for the petroleum industry, but in the last decades, they've been used as salt caverns. So you can man-made caverns, you can dissolve part of these diapirs or salt bodies, and then you can inject CO2. More recently, hydrogen has been injected into these salt caverns, natural gas as strategic reserves. So there's many applications of these salt bodies, not just restricted to the petroleum industry. Most of you will probably know this as well. Salt has a very different thermal conductivity when compared to other rocks, so it conducts heat much more efficiently than other types of rocks. So it can have very profound impacts on the petroleum system. And also for other industries, for example, when you're, and people are now talking more and more about geothermal energy, then salt, the presence of mobile salt can also have a very significant impact on these heat fluxes closer to the surface, where they can be harvested or somehow used for geothermal uses. It's not all fantastic things. When you're shooting seismic, salts can be a very big problem. It basically absorbs most, in a simple, very simplistic way. It basically absorbs most of the energy which is being transmitted in the subsurface, and anything below the salt will be difficult to image, and frequently the quality of the seismic imaging below the salt is worse, and also frequently below around the salt bodies, especially when you have complex salt morphologies. It can be very, very difficult to image the non-evaporitic sediments in a basin. So it often requires quite advanced and more expensive seismic imaging techniques like wide angle azimuth and multi-azimuth and other techniques in order to observe strata below and near the salts. There's also drilling problems. So usually salt is seen as something that you just need to drill through as fast as you can, so you avoid problems. You can have reactive shales within the salt, creating pack-off, wellbore, erosion, and instabilities when you have a lot of cavings. Differential solubility of different types of evaporites, so frequently you need to be constantly adjusting the chemistry of your drilling muds. You can have excessive torque caused by salt creep, well control issues, different pressure gradients above and below the salt and within the salt body. So there's a lot of complications when you're drilling through the salts. And this is, I think, the view for most engineers, and I dare to say also for many geoscientists, that salt is simply something which is useful for trapping hydrocarbons, but otherwise when you have to drill, it's a nuisance. It's something that you just need to drill through. It's not seen as a source of information or something that can be actually useful to understand your basin and your petroleum system. Well, that that is not necessarily the case, and as you will see, we can obtain a lot of useful information from the salt itself. So how can biostratigraphy help for all of these cases? Well, in general, any information you can get about the salt may be useful. For biostratigraphy specifically, what we usually use it for, and there are two main areas where biostratigraphy is greatly used: sedimentation age information, so basically putting sedimentation ages on rocks. That's, I would say, is the primary use for biostratigraphy since its beginnings and still today, at least commercial biostratigraphy. And then you usually can say a lot about the depositional environment, if it's terrestrial, shallow marine, deep marine. So you can do interpretations in terms of sequence stratigraphy. So there's a lot that you can do with biostratigraphic data, but these are the two main areas where it's still used today. It can be used real time on rig sites, for example, for TD calls. If your TD is at a specific stratigraphic interval, you can have a biostratigrapher on sites observing samples real time, and he'll be able to tell you, he or she will be able to tell you if you've reached the depth or the interval that you're searching for, also for casing points. And especially if you're working with deviated wells and you want to keep, for example, within the reservoir interval, then biostratigraphy, what is called biosteering, can be very, very useful. And again, this can be done real time. When you're not at the rig site and you have a bit more time to work with the data, you can use it to calibrate seismic interpretation. So to pick the tops that you're interpreting, you can use it for well correlation, especially when you need to do chronostratigraphic correlation. You can also assess thermal maturation, and we'll see a bit more about this in a minute. And then you can do basin-wide studies, reservoir scale correlation. There's many other things that you can use biostratigraphy for. One major limitation of biostratigraphy, at least so far until recently, is that it's usually restricted to non-evaporitic rocks. So usually the evaporites are simply not studied. Well, if you have the right technique, there's actually no reason why you shouldn't also study the evaporitic sequence. So it all started with the question, can fossils be preserved in evaporites? And the answer to that is yes, they can, or we can also say, let's make salt great again, depending where you stand politically, I don't care. But yes, they can preserve microfossils specifically. Macrofossils, so large fossils, are not so commonly observed, but microfossils certainly. So usually you don't have pure halite or anhydrite or whatever evaporitic mineral. Usually they contain impurities. Those impurities are usually clays and silts, which are blown in by the wind into your salt pan or whatever evaporitic setting you have, or by riverine input. But also if you have any vegetation nearby, then all the spores and pollen and also pieces of wood which are produced by this nearby vegetation will end up in the salt lake as well. If you have any connection with the sea, then any seawater coming in will also very likely bring in dinoflagellates, any microplankton which lives in seawater will also be brought into the salt lake or whatever setting the evaporites are depositing in. So these impurities are composed not just of clays and silts, but they're also composed, in the case that I'm going to show in more detail, by polynomorphs, so spores and pollen, algae, dinoflagellates, microplankton, and other organic particles which can be preserved, and they are preserved in evaporites. I won't go into much detail of other fossil groups, but I know that other research groups have recently also found other fossil groups, specifically nanofossils in evaporites. So there's more stuff to be found in evaporites than we thought before. So we've seen that there's not a lot of papers published on biostratigraphy over evaporites. There's a few, and that was my starting point. Likely, that's my guess. It's difficult to tell what was on the biostratigráphers' minds over the past decades. if they just consider the samples barren, they didn't know how to process them or what happened. But the truth is that there's not a lot of published work on salt biostratigraphy. So actually extracting some fossils from evaporites will of course depend on the regional fossil content. In the case of palynology, we're interested in the organic matter. So this organic matter preservation will depend on the EH conditions of the salt lake, and not just the lake, but during diagenesis and all the geological history. You need to keep reducing conditions. If you have oxidizing conditions, all the organic matter will be gone or be damaged to a point where you cannot really recognize any fossils. But then you also need to have a proper preparation method. So standard preparation methods, as we just saw, don't really work. Most of the evaporitic mineralogies, they don't really react to the hydrochloric and hydrofluoric acid. So you need to find something else to be able to prepare to extract these microfossils, here specifically the polynomorphs. What we've seen is that we actually don't need a lot of sample. So typically we've been working with around 100 grams. So cuttings from wells are suitable. And as we will see in the examples I'll show, we can have information on the depositional age, on the paleoenvironments, and also on the thermal maturation. After quite a bit of time in the lab, and we've tried to refine the method, now we have something like 90% effective success rate, meaning that we can extract organic matter from around 90% of the samples we process. From those 90%, not all of them are productive in terms of recognizing the actual fossils to be able to work out the biostratigraphy, but at least in terms of the method itself of actually extracting the organic matter, then we have comparable success rates to normal sediments, so non-evaporitic sediments. I'll show some case studies where this has been applied. The first one, and this was where it all started, the Loulé salt mine in Algarve Basin in southern Portugal. So in very brief presentation of the basin, I won't go into the details. It's a Mesocenozoic basin in southern Portugal. Like many other Mesocenozoic Atlantic basins, there's a metamorphosed basement, and then you have upper Triassic red beds. And then immediately above the Triassic red bed, you have some, in some stretches of the basin, you have some salt, which is in most places of the basin mobile. And then you have a thick Jurassic carbonate sequence. Evaporites occur right above the red beds, and they are mobile, so that they've been mapped onshore and then also offshore by seismic, in seismic lines. They've been identified. So there's plenty of salt diapirs and other salt bodies which occur near the surface. Well, in the subsurface, and some of them near the surface. And this is where the Loulé salt mine is located. This diapir is very, very close to the surface. It was initially found by water wells that were being drilled, and they found salty water, and then they realized that they actually found a salt diapir. And this is located within the Loulé village, now a city, and the mine is still active today. It's been called the squeeze diapir. This has been published by Davidson et al. A few years ago, and it's bounded by several faults, and the strata around are younger Jurassic carbonates. What is explored there is mostly halite. It's an impure halite containing 4% of clays, 2% gypsum, and 1% of other elements. And what we're chasing is exactly those 4% of clays, which, as we will see, includes not just the clays, but these impurities will also contain polymers. So a bit of organic matter that, if we can extract it, we can observe it and tell something about its biostratigraphy. So in addition to the halite, there's some short sequences about 2 meters of interbedded sediments. These are so you have dirty halites below, and then you have this organic rich shale, dolomitic siltstone, and then a gypsum, which is usually at least partially silicified, so it has this cherty appearance, and then you go into the dirty halites again. And this is observed in different thicknesses, but throughout the mine you find these sequence in several places, always with the same sequence. Sometimes it's overturned, but it's essentially the same sequence. So we sample all of these for palynology. This is how they look. The organic rich shale. In some places it's also silicified, which complicates a bit more the processing, but it can also be done. The dolomitic siltstone, this is how it looks. Not very promising for palynology, and indeed the samples were not that good. Churched gypsum was a bit more difficult to process because of all the strange mineralogies. And then the dirty halite, this is generally how it looks. And these are the impurities. So these pinkish, grayish tones are exactly these impurities, and that's what we were looking for. And then we took a few more samples scattered in some places. The halite has this more banded appearance. So we sampled a few of those around the mine. We processed them for palynology, and we were able to obtain, this is still ongoing. I haven't had the time, unfortunately, to publish this. Hopefully I'll do that soon. So plenty of spores and pollen, and then also a few phytoclasts. Phytoclasts are basically small pieces of wood, which are transported along with the spores and pollen into the saline lake. Another name for phytoclast is vitrinite, and vitrinite is the standard method which is used to determine thermal maturity in sediment. So you basically, in a nutshell, you measure the reflectivity of vitrinite particles, and you are able to obtain a numerical paleo peak temperature. So the peak temperature that was obtained by those rocks. So the method, this was a interesting add-on to the work that we were doing, that you can actually also use not just the spores and pollen and other particles for biostratigraphy, but you can also use these phytoclasts, aka vitrinites, to measure the thermal maturity. So you can have even more data from your samples, from your salt samples. Again, I won't bother you with the names. We found quite relatively diversified spore and pollen assemblage. We found only terrestrial indicators, which, well, I would be careful with the interpretation. I cannot say that this was strictly a terrestrial environment. There was likely marine influence, but very, very restricted marine influence. For most of the time, the only organic particles that were being transported into the lake were of terrestrial origin. In this case, the spore color also gives you a qualitative evaluation of the thermal maturity. There are several scales. Here I'm using the thermal alteration index, which is around 3, and that's in accordance with the vitrinite reflectance studies that were previously done by Fernandez et al. A couple of years ago. And so that corresponds to the late oil window going into the wet gas window. So a lot of data from a few samples that was obtained from a few samples from a mine. The second work that we did, we got some samples from this salt mine in Morocco. In this case, these were not direct mine samples, but from wells that were drilled in the mine or nearby the mine. So we had basically core samples, different types of lithologies, interbedded shales, pinkish halite, brown, black halite, different types of lithologies. Most of the samples were positive. The only ones that were not positive were reddish shales, which is a long known fact for palynologists that these reddish colors usually indicate oxidative conditions, which destroy organic matter. So palynology samples are usually barren. Fortunately, and we found that by testing several samples, the pinkish or reddish colors in halite are not indicative of oxidation, at least not to the point that it destroys organic matter. So pinkish samples, reddish halite samples are also, at least in some cases, are also productive. Similarly to the previous example, we also found phytoclasts, aka vitrinites, and again, in addition to the biostratigraphy that can be assessed with the spores and pollen, we can also assess the thermal maturity using the vitrinite. This, I'm sure several of you already visited this Velitska salt mine. It's now more known because of its touristic beauty. And indeed, it's a beautiful place. But in addition to the beautiful carvings and sculptures and all of that, the geology is also very, very interesting. And last year I had the chance to visit the mine with some of the organizers and some of the people who are attending. And I took some samples from the several types of salts. The Spitze salt, which is basically a big rubble of redeposited salt. So I analyzed the salty shales, which occur in rafts, and other types of lithologies. And in this case, the assemblages were beautifully preserved. So in this case, I think all the samples that were processed were productive. In this case, we found a bit more of marine influence, so not just spores and pollen, and also those phytoclasts, those pieces of wood, but we also found dinoflagellates, so quite diversified assemblage and beautifully preserved. So in this case, the two previous cases, these were early Jurassic salts, and in this case, it's Miocene mobile salts. We also tested this in an abandoned gypsum quarry here in Portugal. So you can observe still some pieces of gypsum which was explored. There are different types of gypsum. Some of them seems to be secondary gypsum. Others seems to be more or something similar to the primary gypsum. Not all of the samples were productive, so the secondary, what seems to be filling some of the cracks and some of the fractures, this fibrous, dirty secondary gypsum was not productive. There was no organic matter, but the gray gypsum, more crystalline, this provided a beautiful assemblage, which was also very nicely preserved. Again, in addition to the spores and pollen, we also found the vitrinite, so we will be able to determine the thermal maturation of these evaporites. Another example that was studied, and the work is still ongoing, from the Klodava salt mine in central Poland. This is Eckstein salt. So we analyzed several types of samples. Again, not all samples were productive. The dolomitic and the reddish lithologies were not productive, but this is a well-known fact by palynologists that dolomites and reddish shales are usually not productive. So there's no really big surprise here. The other samples were productive, so black and gray halides, black shales and siltstones were productive. In this case, the salt was affected by igneous activity, so the organic matter looks very, very dark. So these are the typical Permian spores, and here a phytoclast, a piece of wood, which was preserved. And again, ongoing work, we still need to oxidize this and study in a bit more detail. But this, I think, adds to the evidence that regardless of the age, as long as you select correctly the type of samples and use the correct method, then biostratigraphy on evaporites does work, and you do get relevant results. So concluding, the adapted processing technique is now standardized, so we've been able to, after quite a bit of work in the lab, to standardize the technique. It's varies, so you always need to be aware, at least have an idea of the mineralogy that you have in your sample, and depending on that, the process can be quite simple. For example, when you're working with halides, you can dissolve most of the evaporites just by using hot water. When you get more complex mineralogies and evaporites which are not so easily dissolved, then you may need to use more aggressive chemicals, not just by using hot water. We've also observed that productive sample characteristics, so for example, crystal size, color, etc., are now better understood. Initially we thought that if you had what seemed to be recrystallized evaporites, though, that would destroy organic matter, but apparently it does not. So We processed several samples where we had crystal size quite significant, but still they were productive. Also with color, our previous experience, and that's what palynologists run away from, the reddish colors, they do not work for reddish shales, but when you go for pinkish and reddish halides, they do seem to work. The quality may not be as good as other lithologies, but it still provides productive samples. We've red shales and dolomitic lithologies do not provide good results. Usually, you may have surprises, but usually these are not good samples. Secondary crystallization, so if you look for evaporites in fractures, replacement of other lithologies during early diagenesis, usually they do not preserve macrofossil preservation. We have another case study, which is already a commercial study, where we have very pervasive anhydrite replacement of other lithologies during early diagenesis. And that we found is a killer for organic matter and, well, mostly most other fossil groups. So if you have this kind of pervasive replacement, then it will be very difficult to extract fossils from it, because basically everything is destroyed. But otherwise, it does seem to work. Samples from different ages, geological settings, and thermal maturations provide different positive results. So we've seen early Jurassic, Miocene, Permian examples, and they all seem to work as long as you select the samples correctly and you process them correctly. Then you're likely to have good results. Mobile salts, non-mobile salts, very poorly thermally matured to heavily matured, like the example we saw from the Zechstein salt, then they all seem to work. So I think the main conclusion that this can be applied to any type of sample. So that we also saw, we had mine samples from outcrops, from wells, then all of them seem to work. And in addition to the biostratigraphy, we can have, if we have, and usually we've seen that we have phytoclasts, we can assess also the thermal maturation of your salt. So I've seen, for example, basin modelers struggling how to include the salt in their models. How does that impact the thermal maturation? What's the heat flow that you expect in the salt? So this technique can provide very important control points if you know the peak temperatures that your salt bodies attained. And now I'm wrapping up. This is just an example of, for example, this is the pre-salt of Brazil, where many discoveries have been made in the past. Still, there's a lot of the geology and the stratigraphic evolution of the basin, which is still not known. Here in pink, you have the layered evaporites, so very different lithologies, but you have basically no information. This is one of those cases where you just want to drill through the salts as quick as you can, and you don't get much information from the salt. Well, what if you have a biostratigraphy defined for this sequence, and also some information about the thermal maturity? You could probably define a biostratigraphy of this evaporitic sequence. You could probably have an idea when you're reaching the base of the evaporite, so you can give an idea to the drillers when you're about to exit the salts. So there's a lot of possible impacts of this technique applied to evaporites. So you're basically turning something that you just needed to drill through into something that can provide valuable information. This is just an example, but as we saw in the beginning of the presentation, there are many salt basins around the world and many places where this can be an effective source of information for real-time drilling up to basinal interpretation of and the stratigraphy of the basin. So this is typically what you have. Post-salt strata, you have some information. Then below the salt, you have some information. Although in the pre-salt, there's not a lot of in terms of biostratigraphy, but the vast majority in terms of thickness and also volume of sediments, if you include the evaporites in the overall thickness of the sediments, you basically don't have information on it. Using this technique, you may have a lot of information. So I published something, an introduction to this a couple of months ago in GeoX Pro, if you want to know more and have something to read about it. And before I finish, I just wanted to acknowledge some of my colleagues, Paul Fernandes at the University of Algarve, who I work with the samples from the Loulé salt mine, Hussein from Mohamedia, a rock salt company that provide the Moroccan samples, Stanislav Burliga that helped with that provided the samples from the Zechstein salt mine, and Alexandre Andrade from the Loulé salt mine. So this is also their work. So that's it for me. I think we can now go to the Q&A.
Thank you, Gil. Yeah, thank you. It's really exciting and interesting talk to see these novel approaches. At least for me, it's pretty novel to see how much information you extract from evaporite sequences, and not only biostratigraphy, thermal maturity. So combining both can be really powerful for companies exploring salt basins. So it's a really interesting approach and method that you developed. So yeah, thank you for sharing this with us. So yes, I will start some of the questions and comments. Just bear with me. So I'm going to start from the chat, which I think we have more comments here. Right. So yeah, the first comment is actually from Piotr, like a comment saying, Gil, there are a couple of papers on stratigraphy in the Shelika formation published back in the 60s and later. He can send you references if you want.
That would be great. Yes, thank you.
Yeah, so you can you can liaise with him now to do that. Okay, so the first question is from Natalie Odegarden. Are you able to tell which deposited spores, pollens blew in from far away compared to from nearby?
Well, usually it depends on what you're studying. Usually, yes. For many stratigraphic intervals, you can associate the spores and pollen that you observe with the parent plants. So you can tell if these plants were living in marshes or they were living upland in a mountain somewhere. So you can have an idea of the sources of these spores and pollen. We haven't done that yet for the case studies that we were presenting, but yes, that would be interesting to understand where these spores and pollen are coming from. Yeah.
Okay. Let's see the next one. So for Mark Rowe, Gil, Shelika is famous for the positional reworking of both halite and non-evaporitic class. What did your results show? And a separate question, what is the shortest time span for an evaporite sequence found with your techniques?
Well, so far we haven't been able to study a complete stratigraphic sequence. In one of these cases, for example, the Moroccan mine, because it's non-mobile salt and we have the sequence more or less preserved, we'll be able, when we get around to study it in more detail, we'll be able to have an idea of the time span that the evaporitic sediments took. Probably the same with the Zechstein salts. I know the samples come from different stratigraphic intervals, so we'll probably be able to tell what is the time span between the top and the base samples. So far, we don't have that data, and I think this will be more easily applicable when you have a thick evaporitic sequence, like, for example, the pre-salt plays in Brazil, where it's mobile salt, but you still have the sequence preserved. So you go, when you start drilling, you're at the top of the sequence, and you're at the bottom when you exit the salt. So in those thicker salt deposits, I think it will be easier to understand actual time span with the biostratigraphy. There was a second question. Can you remind me, Leo?
Yeah, the other question was that Shelika is famous for the positional rework of both halides and other non-evaporitic rocks. And
yes,
what did your results show regarding that reworking?
Well, the results so far, they haven't shown much difference. I was expecting to find considerable differences between, for example, the shales or the reworked salts, but so far we haven't found that much of a difference in terms of the assemblages. I do see that some of the samples, especially the shales, seem to have a greater marine influence. So we're maybe seeing a marine incursion, a maximum flooding surface, or something like that in the shales, and that's why you have the dinoflagellates, which are marine, compared to the salt, where you have either no dinoflagellates or not that many dinoflagellates, where you probably had reduced marine influence. So you do see a few changes, but not a lot. Maybe because everything is reworked and you get like a homogenization of all the assemblages. I don't know. But that's an interesting question.
Okay. Right. So the next one was from. Just a second. Yes, from Osma. Sorry, I don't have. From Osmin Vasquez. Is the methodology used to extract palynomorphs from evaporites, such as gypsum, the same as in other rocks? Do you need HF? I don't know what's HF.
HF is the hydrofluoric acid.
Right.
So no, the technique is considerably different. So if we're studying, for example, interbedded shales or limestones or whatever you find within the evaporitic sequence, then you can use the standard techniques, hydrofluoric acid. Right. Still, sometimes it's a bit difficult because frequently you find salty shales or lithologies that have a evaporitic content. So they may have gypsum or halite or whatever other mineralogy. Yeah. So what we found is that for some easily soluble mineralogies like halite and partially gypsum, hot water works very well, at least to disaggregate the sample. Then other lithologies or other mineralogies are a bit more difficult. So if you go into anhydrites or carnelites and other stuff, actually we found that using an alkaline solution a warm alkaline solution is much more effective. So acids don't work. You actually need to dissolve the samples using an alkaline solution. So that's a different way to process it. I know that other people, and recently I've been in contact with other people that are also doing salt biostratigraphy. So I'm very happy that I'm not the only one. And there are different groups in different universities that are now using this, at least for academic projects, that are also using salt biostratigraphy, and they've been able to use different techniques using boiling with water and then the remaining residue, processing for HF, so hydrofluoric acid, that they found that was effective. My experience was different, that acids didn't really did the trick, so we basically used other techniques.
Okay. The next one is again from Natalie Odegarden. Have you used fluid inclusion studies of the salts, such as heating and cooling experiments?
No. So our aim here was just to, well, one, show that the method is effective. We can extract the, in this case, palynomorphs from salts. And now the second step is that's the one which is ongoing now from the several case studies. Actually study the assemblage, provide the sedimentation age, and in some cases also study the thermal maturation, and then start publishing this. So we haven't expanded to geochemistry or fluid inclusions or other areas. We may work a bit with the mineralogy to understand, to refine a bit better what types of mineralogies are more prone to preserve organic matter, and also how they should be processed to extract the palynomorphs. But we haven't expanded more than that.
Okay. The next one from Paulo Ernesto Spegiorin Vieira. Hi, Gio. Thanks a lot for your presentation. It's a new approach, and I like it very much. So yeah, basically, thank you for the presentation. I think pleased to see this new one for Maria Vargas. Could you repeat what is the main problem in Brazil?
So, not necessarily a problem. Simply,
yes.
you don't have much information from. This is the Campos and the Santos Basin in offshore Brazil, where you have these very thick mobile salts, which is here in pink. This, although it's mobile, you still see the layering, and indeed, it's generally the stratigraphy of the evaporite sequence is preserved. It may be thickened and squeezed and stuff in other places, but it's generally preserved. And you have interbeds of different types of mineralogies, different types of evaporites, and you have some shells and other stuff. The information you have about these evaporites is very, very poor. So you know more or less the age of it because you have some control on the post-salt strata, and you have some control on the lacustrine carbonates, which are the main reservoirs in the pre-salt of Brazil. The lacustrine carbonates, you can get some palynology out of it, some ostracods, but honestly, the biostratigraphic control remains quite poor. So any information you can have in addition to what you have now, specifically for the evaporites, I think would be useful to understand better the basin in broad terms. But then very specifically, one of the issues you frequently have when you drill wells in the pre-salt is that you have very different pressures. So when you exit the salts and you go into the carbonates, frequently have very steep pressure gradients. So that originates drilling hazards, and sometimes the wells are lost. So all kinds of drilling problems. This is maybe wishful thinking, but if you can actually have a biostratigraphy of the salt sequence, and you can know it in detail, and you know what assemblage you'll find here at the base of the sequence, usually this corresponds to an anhydrite layer. So for example, if you have on-site real-time biostratigraphy in the rig sites, then the biostratigrapher will be able to say to the drillers, you're about to exit the salt, you're within the last dozens of meters or something like that. So be prepared to change the mud weight, drill bit, casing point, whatever. So that I would say is immediate application of this technique to a real situation when you're drilling. Then in a more broader scale, if you want to understand the evolution, the ages, the sedimentation ages of the basin, the thermal fluxes and all of that, which I believe is still not completely understood for the Campos and Santos Basin, then again, salt biostratigraphy can provide very valuable information for that. So that's something that I'm now trying to make people aware that this is possible, has plenty of applications, both in academic and commercial projects.
Yeah, more of a curiosity from my side. Have you had a chance to apply your techniques in any of those Brazilian salt basins?
Not yet. I'm in conversations with a couple of old colleagues to obtain samples from the pre-salt, right. Not the pre-salt, but the salt of the Campos and Santos Basin.
And what
so
about
hopefully soon I'll be able to do it. Yeah.
What about the African margin, the conjugates?
That would be interesting as well, but there are not that many wells drilled. So I think it would be, at least in theory, it would be easier to find a well which has enough samples that can be processed for palynology in this case. But yeah, of course, the conjugate margin would be also an interesting application of this. Yeah.
Cool. Yeah. Thank you. Next one is from Jihad Rashid. He says, "Thank you so much for your presentation. Always enjoying watching your presentations." He actually have a question about postdoctoral position in petroleum companies. Is it possible for a new PhD with small experience of teaching in university to get a postdoctoral position in these kind of companies? Yeah, I think that's the question. I think that's more a question generic, which is something that we actually working on now is a mentoring mentee program. So that's something that we could probably try to implement and people like that. But yeah, I don't know if you want to comment on that.
Yeah, my comment would be stay tuned for the mentoring program of the salt basins.
That's very
no,
good.
because I don't have an academic position. I do cooperate with universities, both here in Portugal and abroad, but I'm, at the moment I've supervised students, but at the moment I don't really know. My guess is that yes, I think companies like people to be qualified, so you won't necessarily work in your PhD theme, but the fact that you have a PhD and you've worked with a project for a long time, that's the and you know geology in greater depth than a recent graduate would know, then of course that's an added value for someone applying for a job in a company.
Absolutely.
So
I agree.
That's what I can say, I think.
Yes, very good. Thank you, Gil. So the next one from Ruben Perez. Do you have any results from cuttings of mud logging, or do you need a core sidewall core?
Well, for this is generic for any biostratigraphic study working with evaporites or normal sediments, non-evaporitic sediments. Cores and sidewall cores are always better. You know exactly the depth it comes from. You have a better idea of the lithology. It's always better. Having said that, cuttings are also possible to work with, and the commercial project we have now ongoing, we are working with cuttings, so it's also possible to work with cuttings. Yes.
So the next one from Gillian Apps. So it says, "Great talk, thank you. If you do not see marine source fossils in the main halides, would that suggest the incoming brine came from an already hyper-concentrated source?"
That would be difficult to conclude with the data we have. So what we can say with the biostratigraphy is have an idea of the paleoenvironment of deposition. Where exactly the brine comes from, that would be a bit more difficult, and I think their geochemistry will probably be more useful than that. Now, if you find marine polynomorphs, then you are sure that at least some of that brine has a marine origin. I don't see another way to explain how you find dinoflagellates or marine microplankton in your samples. When you don't find marine microplankton, it's difficult to say. So, for example, I was observing in more detail the samples from Morocco the other day, and in all of the samples I found, I don't know, hundreds of spores and pollen, and I found one very poorly preserved dinoflagellate. So that probably means that maybe originally the lake where the evaporites were forming was fed by marine water, but it was a single event. Then anything that was living there died, and any other source of, in this case, polynomorphs, but I'm guessing other types of sediments, not evaporitic sediments, will be of terrestrial origin. So blown away by the wind or by riverine inputs into that lake. So the interpretation is sometimes not very easy to do. So even if you don't find marine indicators, that you cannot exclude that originally that brine came from the sea, or there's originally it was seawater that fed that lake. It's difficult to interpret.
Okay. Okay, so the next one is just thanking you from Natalie Odegaard. Thank you for your talk. I thoroughly enjoyed it. Again, from Maria Vargas. Thank you, very interesting, and she appreciates your explanation about the Brazilian issue. From Jihad, thank you so much for your answer. From Yakov Godin, thanks a lot for the presentation, Gil. We have a couple more from the Q&A. So one from Connor O'Sullivan, great talk, Gil, thank you. Are certain soil lithologies more productive and effective preserving biostrat markers than others?
Well, yes, there are better samples than others, for sure. So, for example, when you have a black shell interbedded in your sequence, then that's an obvious sample to take, because usually that black color or the dark gray is usually indicative of the presence of organic matter. That's what we were looking for palynology. Also, when you have grayish, blackish tones in your halide samples, those are usually good samples.
Okay.
So yes, so if we're looking for organic matter, then we look for indications of that organic matter, be it the blackish limestone or shale or whatever. And also for the evaporites, it also works. But we've seen that it doesn't work exactly the same way as normal sediments. For example, those pinkish and reddish halides, those also provide results, not as good as the other ones, but they also provide results. Okay. So it's just a matter of looking for the right lithologies, but in general, there's from what we've seen, in all cases, there's always at least one type of sample which is productive.
All right. Yeah. Thank you. So the next one from Maria Lorente. Gio, very interesting talk and work. Thank you very much for sharing. One question there: 100 grams of sample is clean of mud? Yes.
Yes. Okay. So sometimes it's tricky to work with cuttings from evaporites because if they're washed, then there's the risk that everything is washed away. So it can be tricky with especially with certain types of muds that you don't have much evaporites left when you're working with cuttings. But generally, yes, it's preferable to work with washed, dried cuttings than anything else. And if you're going through a halide section or an evaporitic section, usually some of it might have been washed away, but there's, at least from that's our experience, there's always something left that you can use. And 100 grams so far has been more than enough, unless you have very pure halide, like white halide, then that will be very difficult to get anything else. But if it's impure halide or other evaporites, then 100 grams are usually more than enough. Yes.
Yeah, more of an also a curiosity for me, maybe a tricky question, but is there any case study that you actually couldn't get any positive results or enough biostrats markers? Any sequence, any evaporite sequence you worked with?
No, some have been more difficult than others, and of course these are this was our test base, let's say. So we took samples a bit. Well, I cannot say blindly because I've been working with Palynology for some time, so I have already a preset idea of what might work. Still, we took quite range of lithotypes, let's say, precisely to test what works and what doesn't. And there were a few surprises, like we mentioned, the pinkish and reddish halides. And now we know that some stuff doesn't work, and we know that other types of lithologies will almost certainly work. So we've processed something close to 40 samples now from different localities, different ages, and so forth. So we were now pretty confident that we know what works and what doesn't.
Oh, cool. Yeah, that's really, really great. I think we pretty much, I have a few more comments. So from Jihad Rashid, I think he asked which zone exactly in Morocco your
so this is the Mohammedia salt mine, I believe. I'm not sure if that's the correct name. I know that's where the company that explores this is based. Then I don't know much about the geology here, right. But I think it's in coastal Morocco, just north of Casablanca.
So between Rabat and Casablanca, I think. Yeah.
I think yes, but
okay,
not completely sure.
Okay, that's fine. The last one is from Regina Daiki. I'm not sure if I'm saying that correctly. Sorry. So yeah, she apologizes. Sorry, I joined a little bit late. What processing techniques were used with the salt?
So I can go back.
All right, that's very kind.
Where is it? So yeah, so for normal palynology, this is what you use. You take a sample, crush it, and then you do two types of acid attacks, hydrochloric and hydrofluoric acid. With that, you get rid of the carbonates, and then you get rid of the silicates. And by then, you got rid of most of the minerals. So you get an organic residue, then there are a few more steps, sieving and stuff like that. What we've seen, but again, other people have developed different methods is that the acid attacks have not been effective, were not effective for evaporite. So they basically put the acid into the flask and it didn't dissolve anything. So for simple or easily solvable evaporites like halite and partially with gypsum, hot water seems to work, at least to dissolve part of it. Then for other lithologies which are, or other mineralogies which are a bit more difficult, actually a warm or hot alkaline solution seems to be working better than an acid solution. So that worked better than the acids. Then in some cases it's useful, for example, to use heavy liquids. So you basically separate organic matter from the minerals by using differences in density. So there's different types of samples will have different types of processing, and it's, you know, we have now a standardized method, but with several branches of it, depending how the sample reacts and depending on the original lithology or mineralogy.
Okay. I think that's pretty much it. We got a lot of thank you comments. You can check them up later. We recorded the talk. And yeah, I want to thank you again for spending time with us and sharing all these cool techniques, very interesting stuff, for answering the questions. Just want to leave a note for the next webinar, which is on October 20th, so 2 weeks from now, with macro, passive versus active salt diaphyries and seeing diapiric strata. So yeah, don't forget to join us. This also seems definitely going to be a great webinar. And yeah, thank you everyone for joining as well. And yeah, thank you, Gio. It was really great.
Thank you guys for the opportunity.
No worries, our pleasure. Thank you. Bye everyone.
Bye.
Take care. See you in 2 weeks.
Bye.